Dear all, we are continuing with the properties of continuous time Fourier transform. The fourth property is frequency shifting property. It states that if the signal x of t is transformed to x of j omega, then e raised to plus or minus j omega naught t into x of t is transferred to x of j omega minus or plus omega naught. That means if you are multiplying the original signal with a complex exponential in time domain, then the frequency domain, the spectrum gets shifted by the same amount towards right or left. Okay, so here if you are multiplying with e raised to plus j omega omega naught, then the shift in the frequency spectrum will be minus, that means towards right. Here if you are multiplying it with e raised to minus j omega omega naught t, then the shift will be towards left, that means your spectrum will be x of j omega plus omega naught. So for plus sign here you have minus, and minus sign here in the frequency domain you have plus sign. Okay, so that is a definition of frequency shifting property. Here also you can prove the property by starting from LHS. So I am taking the LHS, that means the Fourier transform of e raised to plus j omega naught t x of t. I am considering the positive sign. This is equal to integral minus infinity to infinity e raised to j omega naught t x of t into e raised to minus j omega t dt. So here I have two exponentials, first one j omega naught t and second one minus j omega t. I can group these together like integral minus infinity to infinity x of t e raised to minus j omega minus omega naught t dt. If you have j of omega minus j omega t, then your the equivalent expression will be x of j omega. Since here you have minus j into omega minus omega naught, its designation will be e raised to x of j omega minus omega naught. Okay, so if I am multiplying the signal with e raised to plus j omega naught t in the time domain, then the frequency spectrum will be shifting towards right by omega 0 unit. For positive sign, here we are getting negative sign, and therefore I can write if I am multiplying with e raised to minus j omega naught t, then its transform will be x of j omega plus omega naught. Okay, so that is the case with frequency shifting property, and this property is otherwise known as the modulation property of Fourier transform. Another name for time shifting property is the modulation property of the Fourier transform. And the next property is time scaling property. So according to time scaling property, if x of t is transformed to x of j omega, then x of at is transferred to 1 by mod a x of j omega by a. Okay, so if I am taking the proof, so you know what is x of at is actually the time scaled version of x of t. If you are scaling the time, then what? In frequency domain also the spectrum gets scaled. Here if you are if a is less than 0, that means you know if a is a quantity that is between 0 and 1, that is a fraction, then you will be getting an expanded spectrum. Then the signal is not expanded spectrum, the signal is getting expanded, and if a is greater than 1, you know the signal is getting compressed. Okay, so here if in time domain, if you are expanding the signal, then in frequency domain you are compressing the signal. Okay, the spectrum get compressed. And similarly, if you are compressing the signal in time domain, then in frequency domain it get expanded. Okay, so reverse is happening in frequency domain. Okay, if the signal get compressed in time domain, its spectrum get expanded in frequency domain, and this if the signal is getting expanded in time domain, then the spectrum will be getting compressed in the frequency domain. Okay, so its proof is, let's start with x of at. The Fourier transform of x of at is equal to integral minus infinity to infinity x of at e raised to minus j omega t dt. And that is equal to, so here I am going to substitute at as equal to p. Since at is equal to p, I can write dt is equal to dp by a. And the limits also, if t is equal to minus infinity, p is equal to t by a, or it is same as minus infinity itself. And if t is infinity, then also p is equal to t by a, and if I am substituting t as equal to infinity, I will be getting it as infinity. And therefore I can write this as equal to integral from minus infinity to infinity x of p e raised to minus j omega into t is actually p by a. Here t is actually p by a. So I can write e raised to minus j omega by a into p dp by a. This I can write it as 1 by a integral minus infinity to infinity xp e raised to minus j omega by a p dp. Okay, so this is actually representing the Fourier transform of the signal x of p with respect to the basis function e raised to minus j omega by a into p. Then this can be equated as 1 by a x of j omega by a, because see here if you have omega, that means in the exponential term, if this term is omega, then you will be writing it as x of j omega. Here you have e raised to minus j omega by a, therefore it will be 1 by a x of j omega by a. Okay, similarly if you are taking the Fourier transform of x of minus at, or for a negative, then you will be getting like the Fourier transform as, or for a less than 0, you will be getting the Fourier transform as minus 1 by a in x of j omega by a. Okay, so combining these two things, I can write x of at is transferred to 1 by mod a x of j omega by a. So that is the time shifting property. Next you have the differentiation property, that is the differentiation in time domain. Differentiation can be done in time domain as well as frequency domain. So here I am dealing with the differentiation in time domain, and according to that property, if x of t is transferred to x of j omega, then d by dt of x of t is transferred to j omega times x of j omega. Okay, so if you are differentiating the signal in time domain, then in the frequency domain the spectrum get multiplied with j times omega. The proof is, you can start with the inverse equation or the synthesis equation x of t. Okay, so I am starting with the synthesis equation. X of t is equal to 1 by 2 pi integral over omega from minus infinity to infinity x of j omega e raised to j omega t d omega. So this is the inverse inverse continuous time Fourier transform equation. Now if I am differentiating this particular quantity, d by dt of x of t will be d by dt of this. D by dt of this will be what? 1 by 2 pi integral minus infinity to infinity x of j omega into e raised to j omega t d omega into j omega. Okay, this will be into j omega. Now I can write this as equal to j omega by 2 pi integral minus infinity to infinity x of j omega e raised to j omega t d omega. Okay, so here the Fourier transform d by dt of x of j omega is like this. D by dt of x of j omega is like this. Okay, now I am going to take the Fourier transform of d by dt of x of t. D by dt of x of t. The Fourier transform of d by dt of x of t means I need to take the Fourier transform of this equation. Okay, that means what? Actually, this particular d by dt of x of t is j omega by 2 pi into integral x of j omega e raised to j omega t d omega. If I am taking the Fourier transform of this, I will be getting it as j omega into x of j omega. X of j omega. Okay, therefore in general I can write the Fourier transform of nth derivative of x of t is equal to j omega raised to n x of j omega. So that is the case with the nth derivative, Fourier transform of the nth derivative of x of t. So that is the time differentiation. Next we are moving towards the next property known as time integration property. So we studied about time differentiation property. Next property is time integration property. The statement is, if x of t is the Fourier transform of x of j omega, then integral over 2 from minus to infinity x tau d2 will be transferred to 1 by j omega times x of j omega. Okay, so that is the statement of the time integration property. Okay. Now, I am going to prove this. We can prove the statement. For proving this, and we need to take this particular function, that means this particular function like y of t. Let y of t is equal to integral over 2 minus infinity to t x to d2. Okay, that is this one. Now, how I can retrieve x from this is, if I am taking the differential of this equation, that means if I am taking d by dt of y of t, then I will be getting it as what? X of t. So, x of t is equivalent to d by dt of y of t. Now, what is the transform? If x of t is transferred to this, then d by dt of y of t will be transferred to x of j omega times x of j omega times x of j omega. So, if I am taking the Fourier transform of this equation, if I am taking the Fourier transform of this, I can write the Fourier transform of x of t is equal to the Fourier transform of d by dt of y of t. Since x of t is equal to d by dt of y of t, Fourier transform of x of t will be Fourier transform of d by dt of y of t. I can write Fourier transform of x of t as x of j omega according to the statement, and Fourier transform of d by dt of y of t is equal to j omega times y of j omega according to time differentiation property. And from this equation, I can write y of j omega is equal to 1 by j omega times x of j omega. Okay, y of j omega is equal to 1 by j omega times x of j omega. So that is this. But what is y of t? Y of t is this one. That means what? If y of t is this one and its transform is equal to j omega into x of j omega, then the transform of this integral will be equal to 1 by j omega times x of j omega. So hence we can prove the time integration property of continuous time Fourier transform. Thank you.